Okay, so I would like to give a little bit different perspective on this power method. Uh, this is a way of finding the largest eigenvalue. So the key is to evaluate this expression t to the k over v, t to the k times v over lambda 1 to the k. The idea is you want to find the largest eigenvalue of t. I'm going to do this a little bit differently. Let's try to evaluate this, t to the k v over the norm or length of t to the kv. All right, let's do that. Now, if we use this expression here, we have c1 lambda 1 to the k zeta 1 plus dot 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 plus cn lambda k n to the k zeta to the n. If you read Hepburn's book, you can see that these zetas are the eigenvectors and the lambdas are the eigenvalues that correspond to that. Okay, in the bottom, I'm going to put the absolute value. Okay, c1 lambda 1 to the k zeta 1 plus dot 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 plus cn lambda n to the k zeta n. All right. Now, what do I want to do with this? The point is that lambda 1 has absolute value bigger than the other eigenvalues. So this is bigger than all of these. Lambda 2 is the biggest one. Okay. All right. Now, so I can factor out lambda 1 out of the numerator and out of the denominator. Okay. So I'm going to factor out lambda 1 to the k on the top. And if I factor out lambda 1 to the k on the bottom, because it's a norm, it's going to factor out as an absolute value. All right. So I'll take this lambda 1 to the k as an absolute value here. All right. And then in the top, I'll have what's left is, well, let's take out a c1 also. All right. We'll do that too. So this is going to be times the absolute value of c1. That's fine. All right. And then here we have what's remaining here is zeta 1. And then because we're factoring this out, we will be dividing the other terms by this factor. So the second term, recall the second term was originally lambda 2 to the k, c2 times zeta 2. But I'm going to be dividing that by lambda 1 to the k, c1. Right? And that's going to be the same with every other term. The original term for lambda n was lambda n to the k, cn, zeta n. And I'm going to be dividing that by lambda 1 to the k, c1. All right? So that's my vector on top. Then on the bottom, I'm going to have something similar. If I factor out lambda 1 and the c, it's going to be, in fact, it's going to be the same thing, the norm of the same vector. Lambda 1 plus lambda 2 to the k, c2 over lambda 1 to the k, c1, zeta 2 plus dot 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 plus lambda n to the k cn over lambda 1 to the k c1 zeta n. Okay, now I'm going to take this vector here, this extra vector on that's the same on the top and the bottom, and I guess I'm going to call that epsilon vector. Okay, now what do you notice about epsilon vector? Well, epsilon vector is the first term. I can rewrite this as lambda 2 over lambda 1 to the k. So my epsilon vector here is equal to this factor times c2 over c1 times zeta 2 plus, and then the same thing with lambda n over lambda 1 to the k. And then this is going to be cn over c1 zeta to the n. All right. So that epsilon there. So this is epsilon on the bottom also. Now, if you notice, as long as C1 is not 0, since lambda 2 is greater than lambda 1, lambda 2 is less than lambda 1. I'm going to have lambda j over lambda 1 to the kth power. That's going to go to 0. Okay. Since the absolute value of lambda j over lambda 1 is less than 1. Okay. I have to use absolute value because these might be complex or negative eigenvalues. So that means that epsilon, when k goes to infinity, is going to go to the 0 vector. All right. Now, I'm not going to be formal about limits, but you can see intuitively that each vector here is going to 0. So that means the entire vector is going to 0. Now, in order to make this a little bit better, I'm going to put epsilon k here. Okay. All right. So epsilon k is going to 0. All right. So what do I have? I can rewrite this in terms of epsilon k. So if you remember this is TKV over absolute TKV. So let me copy that down here. TKV over absolute TKV. Let me go back up and see what the first term was. The first term was lambda 1 to the KC. I'm just copying what I have there. C1 over lambda 1 absolute value k C1. And then here I have this vector zeta 1. Okay. And then I have plus epsilon k. And then this is divided by the norm of zeta 1 plus epsilon k. All right. All right. Now, I think it's not too far to see that since epsilon k goes to 0, and there would be, that should be a straight here. Let me fix that up. That should be a straight because this is the norm. Okay. It's not too far to see that when k goes to 0, this numerator is going to go to zeta 1, and this denominator is going to go to absolute value of zeta 1. So this, when k goes to infinity, so it's going to be lambda 1 over absolute lambda 1 to the k times, this is going to be absolute, this is absolute value C1. So this is C1 over absolute C1. And then this is going to just go to the zeta 1 over zeta 1. All right. All right. All right. Now, what about this first term here? The absolute value of this first term is 1. Okay. Now, unfortunately, since lambda is complex, this may move around in a circle, but the absolute value is still 1. All of this is a constant multiple of zeta 1. So the result is a constant multiple of zeta 1. Right. Now, I could do this better, but I do hope you can see that if you take the kth power of v and divide by its norm, you're going to get some multiple of the largest eigenvector. As long as k is big enough, these terms epsilon k go to 0, and you get some multiple of the largest eigenvector. So that's the idea that Heffron is trying to make in his book. All right. So that's why you do this process of, let's go there. Here we have this. Sorry, it's not there. We're here. It's similarity, and we're doing the method of powers. That's why you're doing this process of taking the vector, making it a unit. So you're always taking the t times the vector and then dividing it by its norm. Okay. If I just plugged in tw0 here, that would be tw0 divided by the norm of tw0. At every stage, he's dividing t times the previous vector divided by the norm. And that t times the previous vector runs all the way back to t to the k. Okay, so apart from fudging this a little bit, the fact that this number here may not actually converge, but the absolute value of this will certainly converge, right? And the direction does converge, right? The direction converges in the direction of the largest eigenvector. And I want to make the point also that here, when he's doing this process here, he's basically taking t times the previous vector, then multiplying by a constant, and then taking t times the previous vector, multiplying it by a constant. Those constants can come out, and essentially he's taking a power of t times the vector, and then multiplying that by a constant. All right, so that's what's going on here. Now, what you want to do and what you hope is going to happen is that as this process goes, you're going to get V1, V2, V3, and so on. Let me copy his process here. Okay, let's go back there and copy the process. It's right here, so let's grab that. Screen clipping. Okay. Right now, what's happening here? All these W's are unit vectors. Okay. Okay. So what you expect to happen is that these W's may have in two dimensions. These W's may change direction until they're going to settle down close and closer to some direction. Okay. Now, when the process is converging, that means that the difference between these two vectors will become smaller and smaller. So the WJs are converging. So that means that the difference between successive WJs, WJ minus WJ minus 1, this is getting smaller and smaller. And naturally, that means that TWJ minus TWJ minus 1, well, that's the same thing here. I'm going to make straight bars here. That's the same thing as T times WJ minus WJ minus 1. And that's also getting smaller and smaller. Okay, so a way to test convergence, is to evaluate this difference. You could either do WJ minus WJ minus 1 or TWJ minus TWJ minus 1. And see how small it gets. And if it's sufficiently small, then you can stop the process. So I can say when it gets small enough, you can stop the process. Now, how small is small enough? That's what you choose. Okay, right. All right, now I said Wj minus Wj minus 1 or Twj minus Twj minus 1. If you look at his definition here, Twj is just the same as Vj. Okay. So that's the same thing as Vj minus Vj minus 1. So just make that point here that this is or Vj minus Vj minus 1. And please note that all of these are vectors. I'm not going to go back and put arrows over everything, but all the W's and the V's are vectors. Okay, so that's the point behind his exercise here. When he looks at this exercise and he says, redo the previous exercise by iterating until Vk minus 1. Let's insert the screen clipping. Here, let me make sure that's in the right place. Sorry, insert screen clipping. Let me do this. So that's the point here. So he says, redo the previous exercise by iterating until Vk minus 1 has absolute value less than 0.01. This is really not correct. It should be absolute value of Vk minus 1 like this. The distance between those two successive vectors needs to get smaller and smaller. So he's saying when the distance between these two gets small, then that shows you that you're close to the end of the process. All right. Here he chose a small number. For him, this is small enough. Okay. All right. So that's kind of a little bit more background on that power method. If you were confused about this criterion here, and also kind of the derivation here, he kind of waves his hands a little bit. This is a little bit more rigorous. Still, I'm waving my hands a little bit, but hopefully you can see what's going on, that the direction of this quotient does converge, even though the constant may not converge in complex phase, but it does converge in absolute value. All right, so hopefully that helps a little bit.